I more or less had, I guess, what most people would call a midlife crisis when I was 16 or 17 years old. Well, it was all the usual stuff, right? What is the meaning of life? Why am I here? What is my purpose? What, all that. I wasn't worried about how I was going to get a faster car. I didn't have a car, but I was worried about sort of the big questions. And maybe I was lazy, I don't know. Anyway, I had very bad grades in high school, especially, and I did 2 semesters of college and finally flunked out with 17 hours of F and 1 hour of B in physical education. I did that by not taking any final exams, and I joined the Navy and spent 4 years in the Navy and discovered something very interesting, and that is that I like mathematics and science generally, but I really like to create things. I like to invent things. Computers are the only tools that we've invented, really, I mean, excepting possibly the book and relatives of it, that offer direct leverage to the human mind, the thing that makes us a pretty unique animal, at least on this planet. And as such, it's more significant to improve that tool, I think, than many others. A better hoe or a better pencil or a better this or that doesn't have quite the impact. And so the way forward now is with parallel computing. We have really no alternative. It's no mistake no accident, I should say, that our brains are parallel. Now we have the opportunity to reinvent computing, as I say. And the opportunity is essentially covering the space from devices of all kinds up through mobile phones and other mobile devices, laptops, desktops, servers of various sorts, and the cloud, and perhaps beyond, depending. But those different spaces are all parallel computing platforms. The job is to make it possible for everyone who writes programs to write parallel programs. That's everyone who writes programs in one form or other. My approach to parallel computing has been a little bit heterodox from the beginning. I really was presented with a list of problems that are challenging even today to solve. And so a lot of the techniques that I came up with and my colleagues came up with for addressing these challenges were, I guess in retrospect, a little ahead of their time. They were a little bit outside what everybody else was doing. But the idea of latency tolerance, for example, which is now a major, well understood principle, and is been understood by networking people and by queuing theory people for years and years and years. It just hasn't been an architectural principle forever. And the observation that parallelism can be used not only to keep a lot of processors, a lot of cores busy. Parallelism can also be used to fill a pipeline and thereby hide how long it takes for memory to respond, for example, or any other delay to be reacted to. I don't really have to stop and wait for it. I can do something else while I'm waiting. We all do this. We do this in life. Almost none of us leaves voicemail with a colleague that you want to get in touch with and then sits there waiting for the phone to ring. I mean, you don't do that. You find something else to do while you're waiting. You tolerate the latency through parallelism, through having multiple things to do. And that very idea is what lies behind multi-threading, but earlier lies behind multi-programming, lies behind all kinds of ideas that are pretty fundamental in computing. So in a lot of ways, what I did was take a bunch of stuff that everybody knew and applied it to hardware. The fine-grained synchronization stuff is still not well understood. The granularity of parallelism that one can support should be very fine for a number of reasons. Number one, it lets you get parallelism where it's hard to find it, as well as where it's easy. And the more we want to make parallel computing apply universally, in client systems and servers as well. The more we're going to worry about trying to parallelize everything, trying to get everything we can to run in parallel. The other thing, though, that people don't fully apprehend is that compiler technology and translation of programs into machine executable form has diminishing information the larger the scope of the analysis. So if I'm analyzing just a single page of code or a little region of a program, I can do a much more accurate job than I can if I'm trying to analyze a whole program. I can get a lot more reliable information out of it. So if I can extract parallelism at a granularity where the compiler is able to do that, then I can automate the process much better than if I require, very large-scale analysis in order to figure things out or to exploit locality correctly or to do any of the things that we want to do. 20 years ago, a gentleman named Eugene Brooks at a conference called Supercomputing. That year, 20 years ago, it was held in Reno, Nevada. And he got up in front of the audience and said, "No one will escape the attack of the killer micros." His thesis was that the microprocessor was becoming so capable and so fast, and there was so much investment in it because it was mainstream technology, that the high-performance computing industry, the people that are interested in sort of capability computing, which has been parallel computing since the very beginning, really, that whole area was going to be taken over by the mass market microprocessors, by microprocessors intended for client machines chiefly. And of course he was right, and now we see that all of the very fast machines, including the top, really all of them, there are very few machines of any other kind being built today. They're all based on the mainstream microprocessors as components. So I have a new thesis for you, and I call this Killer Micros 2, The Software Strikes Back. And what this is about is the following. Parallel computing is now mainstream. The whole fabric of computing has become parallel computing. And just as the mainstream hardware took over high-performance computing, I think mainstream software will also now take over high-performance computing. What we're working on today is how to make a relatively seamless experience that can run all the way from a personal computer. And let me say, what I mean by that is a computer owns and is dedicated to that person, that sort of concept. Whether it's a PC or a Macintosh doesn't matter. I'm talking about a computer here that is dedicated to a single individual, and yet have the same kind of breadth of applicability for application developers and certainly for solutions to problems that can range up to much more capable machines. Once you get to the point where everything is parallel, then it's only a difference in scale, not of kind. What does HPC mean anymore? Now I think we can take high-performance computing down into the mainstream of industrial America and the industrial world. Eventually what we want to do, I think, is put HPC in the cloud and be able to materialize high-performance computer systems on demand up in the cloud, send messages to them to get them to do the computations I can't do on my local machine, and then get the stuff, get the answer back, and so on. That kind of thing will really spread the use of this, let me call it multi-scale computing. I think a few years from now, we won't call it HPC, but HPC will be ubiquitous. What we'll call it is just plain computing. And it'll be capability computing. It'll be computing that is intended to go fast enough to evaluate the consequences. I mean, in some sense, it's about predicting the future. It's about trying to answer the what-if questions in science or engineering or whatever. And that has been what high-performance computing has always been about. It's just that we're going to push it way, way down into lots of places. Even in the realm of personal computing, even in the realm of computing for the individual's sake, I think we're going to see more applicability of simulation and what if and sort of trying to provide a better understanding of the consequences of our designs and our intents and our lives. We haven't used computers that way much, but I think it's the way we want to use them and will use them, is to try to predict our futures. We have the ability to generate tremendous amounts of data, and the data are valuable. We can learn things from it if we can just get the computing next to the data and get the work done. This is not the traditional way we've done computing, and it's not the traditional way we've managed data. Now what we want to do is actually ship the computing to the data and have the problem to be solved. Ship that to the data and have it done in place without having to move the data and the computing capabilities closer to each other. They're already next to each other, and we just make that happen. This is absolutely at the center of planetary modeling, everything from weather to seismic exploration and all that stuff. Medicine, generally, is becoming more and more data intensive. Life sciences, generally, biology, system biology, proteomics. I never would have thought when I was a kid that I would be enjoying working life at my age and for as long as I can keep doing it. It is absolutely the most amazing time to be in computing that ever was in my life. There are huge currents afoot, and the realization of this vision of general purpose parallel computing is unfolding before my eyes.